Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue on Chapter 5, Part 3, Additions of Alkenes and Alkynes. Okay, so now that we've seen that we have mechanisms we're going to start using for all of these different reactions, we have 5 different patterns to look for. Let's talk about the electrophilic addition to alkenes. In this, we're going to look at the addition of halogen containing acids like HCl, HBr, and HI. We're also going to look at the addition of water, specifically acid catalyzed addition of water to a double bond, and also the addition of halogens to the double bond, Cl2 or Br2. Okay, so the first one we want to talk about is the addition of hydrogen halides or acids to the double bond. Okay, so if we were to take this reaction and just mix an alkene and the acid together, occasionally you have to use a solvent to get them to polarize and react. Okay, when we do this reaction, we actually have what we call a regioselective reaction, meaning that when we add the two together, that we are going to get one of the parts of the halogen, the acid halide, to react with one side of the double bond and one of it to react with the other side of the double bond. Okay, so let's talk about that a little here. If we just added this simple little alkene here, propene, so we can tell the difference between carbon 1 and carbon 2 and carbon 3, and we added HCl across there, statistically, if you just added them evenly across there, you would get half of the time, hydrogen would add to carbon 1, and the chlorine would add to carbon 2, and the other half of the time, hydrogen would add to carbon number 2, and the chlorine would add to carbon number 1. But when we run this reaction, we actually don't see both products. We only see one product. The fact that it could statistically be two different things would make it a regio non-selective reaction, meaning it just reacts whenever it can. Here we actually have it specifically react on specific carbons, okay? Now, this observation led to what we call Markovnikov's rule, okay? Markovnikov's rule states that in the addition of an acid halide, or HX, to a double bond, the hydrogen adds to the carbon with the greater number of hydrogens already bonded to it. By the end of this video, we're going to know exactly why it does that, okay? So let's look at this regioselective reaction again, okay? So using Markovnikov's rule, we can actually predict which side of this acid halide will react, where the chloride, where the halide would be, or where the hydrogen would be. Okay, so if we look at this first one here, and I'm going to draw in blue so we can see it here. So if we're going to add the acid HI, hydroic acid, to the system here, we're going to have a hydrogen end up on one carbon and an iodine end up on the other carbon. Okay, so statistically you could add one to either side, but from Markovnikov's rule, that's stating that the hydrogen is going to be on the least substituted carbon, meaning that this one right here, where our hydrogen's on the least substituted carbon, should be our Markovnikov's product. In fact, it's the only product we observe. We do not observe the other possible isomer. Okay, going back to the reaction on the last page here, this is just propene with HCl. And again, we would statistically have it either side, but because of Markovnikov's rule, it's telling us that the hydrogen is going to end up on here because there are already two hydrogens. There's only one hydrogen on this side, so that our major product is going to have the hydrogens on that number one carbon. And in fact, we do not see the other isomer possible. So Markovnikov's rule is working here. The hydrogens are adding to the side with the most hydrogens. Okay. This also works in acid catalyzed hydrations. Okay, so in the case of hydrations, we're going to be adding water completely across that double bond, meaning the hydrogen is going to go on the one side and the OH is going to go on the other. So when we do this, the hydrogen, because there's a hydrogen here and there are no hydrogens on this carbon at all, that means the hydrogen is going to go here and the OH is going to end up on here, leading to our major product is the one here. And again, the other product is not observed. Okay, so Markovnikov's rule tells us that hydrogen will always add to the carbon with the most hydrogens. All right, let's do some other examples here, okay? Just learning Markovnikov's rule, we can now predict what the product will be here. Now notice that when we draw these skeletal structures, you got to remember where the hydrogen is. In this case here, this is the only hydrogen on the double bond, because double bonds have a total of 3 bonds here. So this is the only hydrogen, which means the hydrogen must end up on that carbon. So I'm going to draw it just like this. The hydrogen was already here, and our double bond used to be in between these 2 carbons here. And I'm going to change it over to red to show you where the hydrogen from the HBr added and where the bromine added, okay? Just using my Markovnikov rule, this is how the molecule must be in the system. Oh, wait, we're missing a carbon here. Let's not forget our other carbon here. We had 2 carbons bonded to it. We have 2 carbons bonded, and now we have our bromine there. Okay, so let's use Markovnikov's rule and add water across that same molecule, okay? So again, we'll draw the structure here, 1, 2, 3, 4, 5, 6. Okay, and remember we have the 1 hydrogen here. In fact, it's the only hydrogen, which means when we add water here across there, that 1 hydrogen is going to go on that same side with the hydrogen, and the OH is going to go over here. Okay, just using Markovnikov's rule, not understanding exactly how the mechanism works yet. Okay, so let's do this one here now. There are no hydrogens on this carbon here, so that means the water hydrogen is going to add to this side, and the OH is going to be on the other side, yielding our product. We have a methyl group there, we have a methyl group here, and we had a hydrogen here on our starting material. Okay, let's add water to it as our red, so the OH is going to end up here, and the other hydrogen is going to end up here. Notice that we have 4 bonds on this carbon now. We started with 3 bonds because it was a double bond, and we now are 3. So we started with an sp2 hybridized carbon, and we ended up with an sp3 hybridized carbon with 4 bonds. Okay. All right, so let's use that last example here to see where we can add it. So in this case here, we have to say, oh, we have 2 hydrogens on this compound here and 1 hydrogen here. You don't have to draw them there, but remember they're there. So that means that our product has to look like H, H, H. And now let's add the HBr in red here. So this already had 2 hydrogens on this side, so the hydrogen has to go to that side. So we're going to add a hydrogen there, which means the bromine has to add on the other carbon. So using Markovnikov's rule, we can predict the major product of these reactions. Now, sometimes you do form the minor product, and I'll show you why. But you can easily predict the major product just by following Markovnikov's rule. Okay, so let's talk about the mechanism and why it adds that way specifically. Okay, so in the case of our compound here, let's use a symmetrical, a symmetrical double bond here. So notice there's a methyl group here and a methyl group here, which means each of these carbons has a hydrogen on it now. Okay, so it doesn't matter which side we add the hydrogen to first, it's still going to give us our Markovnikov's product because the hydrogen is added evenly to either side. Okay, so in this case here, we have a double bond. And in the case of our double bond, that's where our electrons are, right? They're above and below that plane. And we have a hydrogen here, which is a Lewis acid. Remember that Lewis acid wants to accept an electron pair to create a new sigma bond. So if the hydrogen here is our Lewis acid and is accepting an electron pair, that means that our double bond, our lone pair, our pair of electrons is coming from our double bond to give us our new sigma bond here. And when it pulls the electrons away from that carbon, it leaves a positive charge, okay? So the first step is when we add that hydrogen to that double bond, those electrons are used to make the sigma bond to the hydrogen and generates a carbocation, or a positive charge on carbon, okay? So the addition of a proton was one of those patterns to look for in a mechanism. So the second thing that can happen now is, now that our chloride has all the electrons on it, it is now our Lewis base. It can donate a pair of those electrons to whatever our Lewis acid is to create a new sigma bond. And so what's happening here is our carbocation here is now our new Lewis acid. We have our lone pair coming in to create our new sigma bond, and our product of this acid-base reaction is now a neutral species, okay? So let's look at that in an energy diagram, okay? So we have our two starting materials here. We have our HCl and we have our alkene, and they're happy, and we're gonna heat the reaction up until we've achieved enough energy to get to our first transition state, okay? When we get to that first transition state, that's where the hydrogen is coming in to bond to those electrons in that pi bond. And when it does that, it now then goes downhill and generates an intermediate. Remember, that carbocation we can isolate, and therefore it's an intermediate, not a transition state. And once we have that carbocation here, now we have a very fast acid-base reaction, and we have another activation energy to get those two charged species close enough together to actually react to form our new sigma bond, and then it cascades down into products here. Now notice the energy, the potential energy of the products here is lower than the potential of the starting material here, which means it's an exothermic reaction. So that double bond was storing energy, and now that we've got all these sigma bonds, now we've released energy into the system. Okay, so all two-step reactions will have this formation of a first transition, formation of an intermediate, and a second transition until we get to products here. Okay, so when we have two-step reactions, think two steps in our energy diagram. Okay, so let's talk a little bit more about the actual nature of that carbocation. So we started with an sp2 hybridized carbon that had an electron in a p orbital to generate overlap with the p orbital next to it, okay? So the electron that was in that p orbital has now been removed to create the new sigma bond with the carbon next to it. So now we have a vacant p orbital and a positive charge, but we haven't changed the hybridization at that carbon. We still have 3 sp2 hybridized bonds and an empty p orbital that is now specifically reactive. Okay, so again, it is an sp2 hybridized carbon, meaning all its trigonal planar at 120 degrees. The more bonds you have attached to it, though that you have to have at least 3 things attached to it, and the more carbons attached to it, they're actually great. Our unhybridized p orbital is now empty and has no electrons in it, and therefore has a positive charge. Okay, so what that means is now our carbocation is what we call an electrophile. It is seeking electrons to bond to. Okay, and remember, Lewis acids are things that accept electron pairs. So our carbocation can be called an electrophile, or it can be called a Lewis acid. They're basically saying the same things. They are willing to accept electron pairs to form a new sigma bond. Okay, so in the case of our regioselectivity, the reason it's selective is tertiary carbocations are more stable than secondary carbocations. Remember, tertiary is a carbon with 3 other carbons bonded to it. Secondary is a carbon with 2 other carbons bonded to it and a hydrogen bonded to it. Okay, that's important. A secondary carbocation is a little more stable than a primary carbocation, which is a carbon with just 1 other carbon and 2 hydrogens. Okay. Now, we rarely see a methyl or a primary carbocation in solution because they're not very stable. And so therefore, the order of stability goes a methyl, which is 3 hydrogens on a carbon, is very unstable, followed by the 1 methyl group attached to that carbon, or an ethyl cation. In the case of having a secondary carbocation like the isopropyl cation, that's more stable. And this T-butyl cation is the most stable carbocation we can form because it has 3 carbons bonded to that positively charged carbon. Okay, why is it more stable? That's what's next. Okay, the reason it's more stable is we have what we call the inductive effect. And that's basically saying, I have a negative charge here, and to help stabilize this negative charge, I want to pull in electron density from as many places as possible. Okay, This is a trigonal planar carbon, so it is bonded to 3 other things. If it's bonded to 3 other carbons, it can pull a little electron density from each of those carbons, okay, to help stabilize that charge, okay? So it's stabilizing that charge because it's trying to spread that positive charge out over as many atoms as possible, okay? In the case of hydrogen, it only had 1 electron in its outer shell. It's using that electron to make that bond. It has no more electron density to help donate to stabilize that positive charge. All of those carbons have a little more electron density because they are a second shell atom, and they're bonded to hydrogens that can help stabilize any possible part of the charge. So inductively, it can pull a little bit of electron density from all 3 of those, okay? Now, if you only had 2, you can only pull in from 2. If you only have 1, you can only pull in from 1. So the methyl cation is the least stable because it has no carbons to draw from. The methyl is next most stable because it has 1, but it also has 2 hydrogens bonded to it. Then there's the secondary, which has 2 carbons to pull from, and tertiary, the most stable, has 3 carbons to try to stabilize that charge. Okay, now let's go look back at Markovnikov's rule and why it works, okay? Going back to that original compound we looked at, propene, if we added the hydrogen to this bond over here, that would generate a primary carbocation. And that primary carbocation is not very stable, okay? If we had that hydrogen instead add to this terminal one, we generate a secondary carbocation. Secondary carbocations are much more stable than primary carbocations. Therefore, this is the major reaction to happen, yielding our major product. And the fact that this primary carbocation is so much less stable than the secondary, we don't form that product at all. So Markovnikov's rule actually follows the rules of carbocation stability in its regioselective rule. Okay, stay for the next one.